let's continue to solve this OD by Laplace transform. All right, first, let's get some basic formula. Because we need to take Laplace transform on the right-hand side on U function, only U function. Okay? Yeah. So very simple. So we know we have this formula. Okay? Yeah. So that's one. You can use. Yeah. Then, yeah. Now let's apply Laplace transform. Yeah. Here you can see. Yeah. We apply Laplace transform on this I form equation. Yeah. All right. Then, yeah, based on our notation, yeah, Laplace transform of little I function, we use capital I of S function represent. It's Laplace transform. Yeah. Yeah. In that way, yeah, very simple. Right. Then this integral formula, yeah, we have that integral formula, right? Integral formula, that's the capital I function divided by S. Division. Yeah, remember we we observed one correspondence thing. When we take a derivative, we need to multiply S, right? Yeah. First derivative multiply 1S. Second derivative multiply S squared. Yeah. And integral, that's the the opposite operation, inverse operation, right? So your multiplication, the opposite, the inverse, division. Yeah. So based on that, integral of this function, you take Laplace transform, you just do the division by S. Yeah. Very simple. Yeah. Yeah. So in this way, you can see by the Laplace transform, we can handle the integral easily, right? Otherwise, to solve this equation with integral here, too hard, right? Yeah, so very hard. Yeah, yeah. Here, so it becomes an algebraic equation. Yeah, algebraic equation. Yeah, all right. So then let's solve this algebraic equation for capital I function. Yeah, pretty straightforward. Yeah. Yeah, so I function equals this part constant, right? Yeah, big fraction, but all constant numbers. Then, we only need to do the inverse Laplace transform on this part. Yeah. Okay? Yeah. All right. Yeah. So, yeah, although sorry. Yeah. Oh, sorry, it's not constant. There is an S here, little s. Yeah. So we single it out, S. Yeah. Then the other constant. The constant part, there is S. Yeah. So it's different. Yeah. So now let's do some analysis. How do we apply inverse Laplace transform? Yeah. For the E part, we have second shifting theorem, right? Yeah, the numerator, yeah, so here, two fractions, so you multiply out. So two fractions, yeah, each one, the numerator you have E function, yeah, so that E function, we use second shifting theorem, so we can take care of it. Now, we do not need to consider the E function part. Then, inverse Laplace transform, yeah. Here, S plus some constant, we need to apply first shifting theorem, right? Another shift operation at the S, yeah. S side, yeah. So you need to apply first shifting theorem, yeah. Second shifting, first shifting. Although very simple, yeah. 1 over S, inverse Laplace transform 1 over S. Inverse. Yeah. Constant, right? Yeah. Actually, yeah. So that part, yeah, we need to. Yeah. All right, so here we use capital F, yeah. So then, shifting theorem. We need, yeah, so this whole fraction, we use capital F. But we need to take inverse Laplace transform on capital F. All right. Yeah. So this basic formula, inverse Laplace transform of 1 over S is 1. Is 1. Yeah. All right. Yeah. Then shifting, when you do shifting, we need to multiply E function at the T side, right? Yeah. E. Yeah. Yeah. Because here, S, there is a constant shift. Then we need to multiply by the first shifting theorem. We need to multiply E to the, A constant, right? Yeah. So you have a constant A. Yeah. All right. Yeah. This is the first shifting theorem. First shifting theorem. Yeah. Minus A. Yeah. So because this is a positive number, plus positive number, minus A, your A is a negative number, right? Yeah. Negative. That's 1 over capital RC. Yeah. So E to the A is a negative. Negative 1 over capital RC times T. Yeah. All right? Yeah. So in that way, so this is the second shifting theorem. This is second shifting theorem. First shifting theorem, second shifting theorem. So we can calculate that, little I function, inverse Laplace transform of capital I function to get the little I function. All right, so so here I use because, not enough space here. So I move to a new slide to get more space to do the last round calculation. Yeah. All right, so now we are here. Okay, yeah, we are here. First, let's calculate this part. Yeah. First shifting theorem, right? So basic formula number 1 and first shifting theorem. Okay? Yeah. Yeah. All right. Yeah, so here, just some small simplification. Yeah. All right. Yeah. Take the constant, numerator constant out. Yeah. All right. Yeah. Then E to the negative, because A value, A is negative, right? A is negative. So AT, so E function exponent is AT, so negative T over capital RC. Yeah. So this is the little f function. So we get little f function, okay? Yeah. So next round, we can apply the second shifting theorem. Yeah. Second shifting, because we have this little f function. Yeah. So each term, yeah, so f, so you multiply through, you have, 2 terms. Each one, you apply this second shifting theorem. All right. Yeah. So little I function, yeah, inverse, yeah, so, inverse of these two terms. Yeah. Then, second shifting theorem, you have the little f function. Yeah. Little f minus a, yeah, so then you plug in, so you get into the little f function. Yeah. So the specific, the expression is like this. That's your final solution. Okay? Yeah? Yeah. For the final solution, you need to use Heaviside function in your final solution. Yeah. Here. So here you can see we use the 2 shifting theorems quite a lot. So first you need to identify, based on the structure of the formulas, you can identify. So on the worst situation, you should apply second shifting theorem. On the worst situation, you should apply first shifting theorem. Then definitely you need to, get familiar with the basic formulas. Yeah. 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 So then you can see this Laplace transform is a very powerful tool solving ODE. Yeah. They're very powerful. mainly, what do you need to do? Algebraic operations. Yeah. You never need to do derivatives, integrals. Yeah. Algebraic operations. Yeah. Yeah. Okay. All right. Yeah. So one thing. Yeah. Remember, in our previous slide, we have a Q version, right? Yeah. So, you know, later, when we have the electric circuit problem, so we will use the Q version to do the calculation. Yeah. So here, R, Q, this is the little q version, and Q equals, yeah. So another way we can apply Laplace transform on this Q form ODE directly. So we get a capital Q, right? Capital Q, you know. Yeah. The differentiation, we have that formula. Yeah. S times capital Q, right? Yeah. But you need to have initial value. So here, you know, initial value is not given. Initial value. Yeah. 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 But, so there is some initial value, the difference. Yeah. Because when you apply that formula, you need to use the Q0, initial value. Oh, what is Q0? Yeah. So here I'm talking, because based on our differentiation formula, when you apply Laplace transform, you need to have the value of Q0. Can you see Q0 equals 0? Yeah. Yeah. Because from the integral, Q of t equals 0t when t equals 0, it's 0, right? Yeah, because when t equals 0, the integral is 0. Yeah. So that part, even the question, you do not have that part. Yeah, but we can easily get that initial value of Q function. Yeah. So you can apply, you know, Laplace transform. Yeah. Yeah. S times capital Q. Yeah. Right. Capital Q. You know. So you can easily find the capital Q. Then inverse Laplace transform, you can find the little q function. Okay. Yeah. But if our goal we calculate the little I function, you just take a derivative of Q function, you get an I function. Yeah. That's another way. So, since both ways should work, you should get the same result. Yeah. But in our specific problems, when we choose one of the two ways, we want to pick the easier one. Yeah. Sometimes one way could be easier than the other one. If both the same difficulty, then just random pick. Yeah. All right. So that's another example. Yeah. All right. Next, now we are ready to solve PDEs. Yeah. So after a lot of practice, so we get familiar with Laplace transforms. Yeah. Now, we want to apply it to solve semi-infinite string problem. Yeah. Semi-infinite string problem. Yeah. All right. Yeah. First, let's get the problem. Yeah. And we try to solve it. Semi-infinite string. Yeah. Find the displacement. Yeah. So here we use W function. Yeah. because after we use U function represent Heaviside, we try to avoid to use U function, because we will get confused if we still use the U function. So here we use W function. All right. Condition. First condition, the strain is initially at rest on the x-axis from 0 to infinity. So that's why semi-infinite, starting from 0, then infinity. All right. For the left end of the strain is moved in a given fashion, namely, the function. Left end of the strain. What's left end? When x equals 0, that's left end, right? 0, left end. Right end, infinity. Infinity, right end. Left end is 0. So the 0, you should have a t function, right? How does the string move at the left end? You should have a function, right? So the function according to a single sine wave. That's the left end function. So this is single sine wave. So we saw it before. But this function is used where x equals 0. X equal to 0. All right? So that's our first condition. W of 0t equals this single sine wave function. That's the second condition. Third condition, right end. X goes to infinity. W of xt, its limit equals 0 when t greater or equal to 0. Here you can see two variables. There is one variable, t variable. Another variable, x variable. Two variables. That's why we consider partial derivatives. Two variables. All right. So we need to solve this problem. So the goal, we need to find this displacement function, W. All right. And here, there is a modeling part. So the modeling part. Here, I skip that modeling part. I just get to the PDE. Because for this system, so there is a PDE derived. But after the modeling step. So we jump to the PDE directly. So later, so if we can find some time, we can talk about the modeling. All right. So here, our main purpose, we want to solve PDEs by Laplace transforms. That's our main goal here. Okay. So after the modeling step, here we skip that modeling step. Okay. Because it's a pretty long story. So to save some time, we jump to the PDE directly. We need to solve the wave equation. The PDE, the special type of PDE called the wave equation. Heat equation, wave equation. So here we consider the wave equation. So this is, the spring, the system corresponds to the wave equation. So this is the wave. Second partial derivative of W. So with respect to t, left-hand side, right-hand side, second partial derivative with respect to x. This is the wave equation, some constant c squared. That's the wave equation. C constant given some other constant. All right. Boundary condition. So this is a boundary condition, right? This left end, that's boundary. Boundary of x. Yeah. X-axis. There are two ends, right? Boundary. So we need a condition at the two ends. Left end condition, right end condition. So the boundary condition, the first one, the second one. That's the boundary condition. Then initial condition, right? Yeah, yeah. Because the string is initially at the rest from this. So initial condition, 0, right? Initial condition. So when t equals 0, initial condition is 0. Yeah. All right. And at the rest, we interpreted its derivative also 0. Initial condition. Yeah. Because second partial derivative, you need a derivative. First partial derivative, initial value. Otherwise, you cannot find a solution for this, second partial derivative solution. At the rest, initially at the rest, yeah, so we can also understand the derivative, partial derivative also 0. All right. Yeah. Yeah, so that's all the conditions. All the given conditions. Next, we need to find a solution for this PDE. Yeah. And we have the Laplace transform as the tool. Yeah. So now we are ready to apply Laplace transform. Yeah. All right. But here, so let me explain this one a little slower. Yeah, because here, it's not very easy to understand. W function has two variables. Your partial derivatives, you have, two different partial derivatives. Yeah. And when we apply Laplace transform, we can only apply it on one variable. Right? Yeah, because by the definition, only one variable. We cannot apply on two variables. Yeah, so it's one variable. So we need to select t variable or x variable. Yeah. Yeah. So we need to do it carefully. Yeah. All right. So that's the, current information. When we start, we take Laplace transform with respect to t. Okay. Not on x, on t. Yeah. T is the variable. So from t, Laplace transform, we get an s variable. Okay. Yeah. X part, we treated the constant part. Yeah. Yeah. When we work on t, we treat x part constant part. Yeah. All right. Treat x as a constant. All right. Yeah. And we need to use the formulas. Yeah. These two formulas. All right. Yeah. Here, second derivative. So we need to use the second formula. Okay. All right. All right. Then we apply Laplace transform on our PDE directly. Yeah. Left hand side. Yeah. Left hand side. T with respect to t double prime. Yeah. W double prime. Yeah. So s squared times L of little w s, yeah, initial condition, right? Yeah, initial condition given. Yeah, all right. Yeah, yeah. Right. Yeah. So initial condition is 0. Yeah. So the good thing is the last two terms gone. By the initial condition, the last two terms gone. Yeah. So you only have So you only have s squared times L of little w. So you have that. Yeah. Okay. Yeah. So then we use capital W function to represent the Laplace transform of little w function. Yeah. Capital W. Yeah. Then, so we can rewrite. So this function s squared times capital W. Then, yeah, this one, yeah. here, this part, we need to do some work. Yeah. This part, we need to do some work. Yeah. L of second partial derivative of little w, yeah, over partial, with respect to x. Yeah. All right. Here, we know Laplace transform, it's an integral, right? The definition of Laplace transform is an integral. Yeah. Derivative, second derivatives on the inside function and integral outside function. Yeah. Here, we need to use a special operation here. Yeah. All right. Yeah, so here, that's based on that special operation, we can switch Laplace transform with the partial derivatives, so we can move Laplace transform inside partial derivative to get a capital W. But the question is why we can do that. Yeah, I need to explain why it is legal to do that. That's under certain condition we can do it. Not always we can do it. Yeah. So the general principle is like this. When the W function is good enough, you can do the exchange. Yeah. Not too bad. Yeah. So if the function is very bad, then you cannot do it. Yeah. If the function is good enough, yeah. Yeah. The good thing is, for our typical engineering problems, our solution functions usually not very bad. Yeah. Solution functions satisfy the condition. Yeah. All right. So here we need to do this interchange operation, interchange, differentiation, and integration. We need to do this. Yeah. Interchange. There is a theorem. Yeah. Theorem we can apply. Okay. Yeah. Yeah. Continuous. Yeah. So. Second derivative. Function continuous. Yeah. So there is some condition there. Yeah. But here, we do not get into the detail. So we just assume our solution function is good enough to allow us to do the interchange operation. Yeah. Yeah, not too bad. Yeah. If it's good enough. Yeah. Not because people can create some radical change, yeah, that kind of thing. Yeah, it's possible. Yeah, but for the functions, not too bad. Yeah, so we can do this. All right. So after we can do this, now here you can see after this, s squared times capital W equals, although it's a second partial derivative with respect to x, can we treat it as an ODE? If we treat W as one function, yeah, just the one function, and in this equation you only have partial derivative with respect to x, no other partial derivative, can we treat it as the ordinary derivative with respect to x, right? Because we treat t as constant here. In this place, so this W function, inside this W function there is a s, right? So not t, s. We treat that s as a constant. Now we treat that as a constant. Then this equation becomes ODE. And we know how to solve ODE, right? Yeah. So here after we solve second order ODE, very simple ODE. Yeah. We know how to solve. We can find the capital W function, right? Yeah. After we find the capital W function, we take inverse Laplace transform. We can find little w function, right? Yeah. So we can do it. Yeah. All right. So let's do the calculation work. Yeah. Now we have a new ODE, yeah, this time. Yeah. So we treat it as ODE. Yeah. All right. Its form is a PDE, but because the too simple, so we treat it as ODE. Yeah. This is a homogeneous, right? Second order homogeneous ODE. So we know how to write its general solution, right? Yeah, we know how to write its general solution. Yeah. Characteristic equation. Two roots. Characteristic equation. Then we can write the general solution immediately, right? Yeah. So the general solution W, yeah, X, S, yeah. The constant part, yeah. Remember, we treat S as constant, right? Yeah. When we solve this ODE, we treat S as constant. Okay? Yeah. All right. Yeah. Here I think the characteristic equation, everybody knows that, right? Here I skip that part because I believe everybody is familiar with. Oh, yeah. Why I get out? Yes, but I need to keep. Yeah. But I need to. Yeah, get back. Yeah. Get back. All right. Yeah. Then move to the place. Yeah. Move to this place. All right. So here, to solve this ODE, yeah, because we know the characteristic equation lambda square minus S square over C square equals 0, right? Yeah. So 2 lambda 1 equals S over C. Yeah. Here we assume, yeah. So here, yeah, because this C comes from here, so we assume C is positive. Yeah. All right. So lambda 1, lambda 2 equals negative S over C. Then we can write the general solution like that, but in our general solution, remember, usually we use C1, C2, right? But here, because we treat S part of the constant, so when we write C1, C2, we should include the S part. We should include the S. Yeah? Yeah. If you use constant, some constant without S included, then you will miss something. Yeah. So that's why we need to do some adaptation here. So not really pure constant. So the so-called constant, yeah, here. Yeah. So we need to, adjust our thinking. The so-called constant, two constant, but we need to include S part. So we use capital A of S and a capital B of S. These two unknown functions, we need to determine these two unknown functions. Appropriate. Yeah, we need to, based on the given condition, we need to find these two unknown functions. Yeah. Yeah. All right. So then let's move to the next slide to determine these two functions. All right. Yeah. Now, yeah, here let's plug in x equal to 0, plug in 0. All e terms gone, right? Because it's 1. So W of 0, but the question, how do you get a W of? How do you get this? So here we know W of 0S equals capital A of S plus capital B of S. But we only have little w condition, right? Little w, yeah, condition. But we don't have the W, capital W of 0S. So we need to calculate it. We need to calculate W, calculate the condition. All right. Recall, yeah. So our W function is the Laplace transform of little w function. Yeah. So if we put a 0 at x in this capital W, we should put a 0 inside this Laplace transform of x, also 0. Put it inside. Because when we do the Laplace transform, we treat x as constant, right? Yeah. Here the constant is 0. We treat x as constant. Yeah. So it's 0. So now let's do that simple calculation. All right? Yeah? Yeah. So plug in 0, yeah? Constant, yeah? No problem, you do it. All right? Yeah. But what is this Laplace transform of this little w? Because that little w, by the boundary condition, right? Left boundary, little f. Little f is given. So it's a Laplace transform of little f function. It's known. Yeah. Yeah. Little f function, single sine wave function, right? Yeah, single sine wave function. So we can calculate its Laplace transform. Single sine wave function. How to calculate? How to calculate? Single sine wave. We know how to calculate sine function, right? Laplace transform of sine. But here it's a single wave sine, not the whole sine. Heavy sine function. Multiply heavy sine function. Right? Yeah. See? Yeah. So now you know how important is heavy sine function, right? Yeah. Useful. Here. All right. So we can calculate it. Here we use capital F represent its Laplace transform. Yeah. When we need it, we can calculate it. We can find it, right? Yeah. All right. So let's use the symbol first. Simplification. Yeah. Now we need to do the simplification. Yeah, because we have that. So capital A of S plus capital B of S equals capital A S of S. Okay? Capital F of S. That's the first equation. This is the first equation. Yeah. Not enough to find the A function and the capital A function and the capital B function, because of one equation, two unknown functions, right? Two unknown functions in one equation. So you cannot find each unknown function. Not, yeah. So you need another equation. Another equation about capital A, capital B functions. Yeah. Two equations. But we haven't used the right end condition, right? Right end condition. So if we apply Laplace transform on the right end condition, can we get a second equation about capital A function, capital B function? Yeah? So we need to apply the right end condition, Laplace transform. All right. Yeah. Yeah. So here, but when we apply, there is a limit, right? So limit. So we need to be careful when we take the limit. All right. Yeah. The definition of W function is this integral. Yeah. So just definition. But here, because we need to take a limit, so in this integral, we need to make x goes to infinity. That's another special operation we need to consider. Okay? The question is, when you take the limit when x goes to infinity, how do you know? You can take limit inside the integral, right? Yeah, yeah. Because for the given condition, you may need to take the limit inside the integral. The question is it legal? Yeah. Yeah. Similar to in our previous slide, when we interchange differentiation and integral, we need some condition on the integral function, right? Here the same issue. We need some condition on the integral function. Yeah. if the function is good enough, we can do it. If the function is extremely bad, then we cannot do it. Yeah, so there is certain condition. Yeah. All right. So here, yeah, because here we need to take the limit. Okay? S goes to infinity. This limit, we want to interchange the limit with this integral. Because limit operation, integral, two different operations. How can you interchange, right? Yeah. There must be some condition. Yeah. So if the integral function is good enough, then we can interchange. Okay? Yeah. If it's extremely bad, then we cannot. All right? So here we assume our integral function is good enough. Yeah. Yeah. But because the real world problem, usually we have the function is good enough. Yeah. All right. So after interchange, take limit, that's 0, right? Yeah. So this will give us interchange limit integration. If we can do that, then the limit of this w, x goes to infinity, it's 0. Yeah. So here that means when you make the x to infinity, your capital W is 0. That's our second equation. Okay? So our second equation, we need to make x goes to infinity. Okay? X goes to infinity. All right. When x goes to infinity, remember, little s is positive, little c is positive. Yeah? So we assumed before, right? Little s positive, little c. So this is negative number, right? E to the negative infinity, right? E to the negative infinity, the limit is 0, right? Yeah? So the second limit is gone. Okay? Second limit is gone. Okay? All right? Yeah. How about the first limit? The first limit. All right? Yeah. Capital S positive, sorry, not capital S, little s, positive constant. We treat it as a positive constant. Right? Yeah. Little c positive constant. X goes to infinity. Positive infinity. Okay? So this e part goes to infinity, right? Yeah. E function goes to infinity. E function goes to infinity. Multiply a of s equals w. W is 0, right? So what conclusion can you get? This e function, goes to infinity. A very large number. Multiply a of s. A of s, you treat a of s as a constant. A of s, when you fix s, it's a constant. A of s is a constant. Constant multiplies some very large number. Suddenly, it equals capital W. We know capital W, its limit is 0. It's 0. So what conclusion can you get? 0. Must be 0. It is forced to be 0. Only when a of s equals 0 for all s. For all s everywhere. Then you can have that condition. So that conclusion. Yeah, because we fix s. Yeah. So and you have this capital A of s is 0. Okay? For all s. Yeah. Yeah. Then you go back to the W expression, S, A term is gone, right? Yeah. You only have B term. B is known, right? So the B, because here, A0, A gone. Yeah, so here. Yeah, let me just draw, A of S is 0. So then B of S equals F. Then A term is gone, W. So your W function is very simple, right? Yeah, so So at the end, your capital W function is this. Very simple. Okay? Now, we can do inverse Laplace transform on S. Yeah, on S. We treat X as constant. When we do inverse Laplace transform, we treat X as constant. Okay? So the last step, little W function equals inverse Laplace transform on this capital W function. Yeah? Is there some shifting theorem? Second shifting theorem. Yeah? Look at the form. Second shifting theorem. right? Heaviside function, right? Yeah, yeah. So second shifting theorem using Heaviside function, little f. Yeah. So we know little f, right? Little f. All right. Yeah. Yeah. So yeah, a, yeah, the shift by that a is x over c. So then you can last to your final solution, little w as this function. Yeah, yeah. I think, look at this example. Yeah, yeah. So we know if we write explicitly, yeah, because that single wave explicitly, yeah. So here I just put the the interval. All right. Yeah, yeah. Some detail here. Yeah, I put some detail. Yeah. I mean just write the interval clearly. Yeah. All right. Yeah. Yeah. But here you can see. Yeah. So here you can see how powerful is Laplace transform. Yeah. We apply to solve PDEs. Yeah. Yeah. All right. Yeah. So let's stop right here. Next time I have another example. Yeah. Solving heat equation. Yeah. This one is wave equation. Next one we will solve the heat equation. Yeah. Then I will, after I complete the heat equation, then I will go back to complete last 2 slides of part E. So then we finish module 2. So next time we can start module 3. Yeah. Yeah. All right. Yeah. Oh, yeah. This weekend I need to post homework assignment number 2. Yeah. This weekend. Yeah. A lot of things. I also need to post the solution to exercise questions, and also grading your first homework assignment. Yeah. Yeah. Oh. Yeah. Did I give you a second? No? Oh, I thought, yeah, we should have second quiz. Oh, yeah. Yeah, I will give you a second quiz. Yeah. Yeah, I thought, I haven't. Yeah. Yeah, because too many things. So, yeah. All right. Yeah, I will give you a second quiz. Yeah, thank you for reminding me. Yeah.
Thanks, Mark.
Yeah. Yes. Yeah. Yeah. Now we cover more material. So our second quiz can cover this part E. Yeah. Yeah. If I give you last weekend, then I cannot include part E.